has a mass of 165 pounds of mass. We want them, so that's going to be relevant. The mass of a ball, of one ping pong ball, equals, let's say it's 10 grams. I don't know. The mass of one ball, we'll take it to be 10 grams. And we'll assume this is about the right size. Let's take it to be 6 centimeters. The diameter of one ball is 6 centimeters. So the question is, how many balls to stay dry? Okay. I think you guys have all the numbers you're going to need. All right. So take a second, try to work out your answer, and then talk to the people near you. Sapon, can you see the board clearly enough today? So, what's the first thing you should do in this problem? Draw what? Free body diagram. Okay, so for what? For the water, for the balls, or for the person? For the balls. Draw a free body diagram for the balls. Okay, what are the forces that act on the balls? What do you have? They have a mass, so you know they must have weight. Okay, what else acts on the balls? The person. It's really the normal portion of the person. It's not really the weight of the person, but numerically it's the same. Okay, so those are pushing down, and then pushing up is what? The buoyant force. Okay, so first get your free body diagram. Everyone should have that drawn on their page. Make sure you have that. Identify the forces, draw the free body diagram. Yes?
That's a 3.3? No, that's a 2.2.
2.2. 3.3 is the conversion from meters per second to feet per second, roughly. So 1 pound of mass is equal to, 1 kilogram of mass equals 2.2 pounds of mass. Remember that. 1 kilogram equals 2.2 lbm. How do I know that it's lbm and not lbf?
Because it's mass, not
Yeah. I can't equate things which are physically different properties, right? You can't equate a force with a mass. They're just categorically different. Sometimes you can relate them, but that's different than equating them. Okay. So raise your hand if you have your free body diagram. Yeah, there should be 3 forces on it. Remember, you don't double up any arrows. If there are 2 forces, you draw 2 arrows. You just don't be stingy with them. There's no shortage of arrows. One more. The weight of the person, most of the balls themselves. They would have a weight.
Oh, that's what I meant. The weight and then just the grip.
Oh, so the 2 different ones.
Yeah.
So they need 2 arrows. Put this up. Yeah. I can just tell you what will happen is if you have 1 arrow, you know you intended it to mean 2 things. Eventually, something will disappear.
Yeah.
So make sure you put it.
Okay, so let's have a good free body diagram. Right? Going down, I would have it's really a normal force from the person. And then I would have going down, just shifting it over so you can visualize it or see it, the weight of the balls. And then going up, we'd have the buoyant force. Is that okay so far? Now, now I need to come up with formulas for these things. So let's start with the weight of the person, or the normal force of the person, but that numerically is equal to the weight of the person. So the normal force from the person equals what? What's the formula for that? Mass times gravity, and I'm going to do everything in metric units, so I'll have to do some converting here. So it's going to be mass of the person times g. So you've got to convert that. 75. Right. So 75 kilograms times 9.81 meters per second squared. It'll come out in newtons. So 735 or so. 740.
735.
735 point. That's. I don't have any more accuracy than that. Newtons. Okay. So we understand that one. What about the weight of the balls? Right? So what's the formula? Tell me what to write.
10 G over 1,000.
Okay, so 10 grams. Okay, so that's going to be 0.0. No, 10 grams is 0.01. 1 gram would be 0.001, and we've got 10 of them. Okay? Times G. Am I done? Weight of the balls. Plural. So how do I account for that?
X.
Yeah. Remember, that's what I'm trying to find, is how many balls. I need to work that unknown into the mix, or else I'll never figure it out. So it's good that we don't have that information. That's the point. Okay. So I'm not gonna call it X, since it's a number. I'm gonna call it N. Okay, so I'll call that N for NB for number of balls. Okay. You just have to invent something. Right? You are engineering a solution to this. You have to come up with, identify the variables that are physically relevant and solve for them. Okay. And then what about the buoyancy force? How do I figure that out? What's the formula for the buoyancy force? What's the idea? Rather than saying formula, physically, what does the buoyancy force evaluate to, or what is equal?
Density of whatever versus water.
It involves density, but say that's more the formula. That's like, what this times this times this. I'm saying, what is it really? It's equal to the blank of blank, which has been blanked. The weight of the fluid that has been displaced. So you figure out, as the balls submerge, figure out how much fluid has been pushed out of the way. And it'd be the weight, and then figure out the weight of that amount. And yeah, when you go to write a formula, you can, depending on the information you give, you might write it with density. It could be you're actually given the mass displaced, or you're given, whatever. But what the buoyancy force is the weight of fluid displaced. Usually you use the density to figure that out. But okay, if you didn't, maybe the problem will give you different information. So you got to know that. All right. So what this is going to be, in this problem, we know the fluid is water. We're going to assume a standard density, which is what for pure water?
So,
1,000 kilograms per meter cubed. Okay, so we will use that number a lot when we're just coming up with problems. So it'll be one to kind of know. All right, so the force, the buoyancy force, evaluates to the, numerically, it's the same as the weight of water pushed out of the way. So that would be the, let's see, so it'd be the density of the water, which is 1,000, times the volume displaced. Okay? So now let's plug in some numbers. Tell me what to write. What's the 1,000? Yeah. Kilograms per meter cubed. Okay, that's the density. Volume displaced. What do I write?
the volume of the balls times the number of balls.
The volume of one ball times the number of balls that are there. Okay, so the volume of one ball, okay. Well, what shape is this? Sphere. And we all know the volume of a sphere, correct? Oh, good job. Hey. Well done. All right. 4/3 pi r cubed, or that'd be 4/3 pi times the diameter cubed over 8. So you could say it's 6. It's a 6. Pi over 6 times diameter cubed. Since I gave you diameter, that's all. I'm just saying diameters. Gives me half and I cube it.
Couldn't you just say, pi times 3 cubed?
Pi times
The diameter is just how that, or put it through the meter.
Yeah. Oh, am I done? Density times the volume. Number of balls. Okay, so I know the diameter. It's over here. I made it really small for you. I'll help you out there. Yes, you're absolutely right. There should have been a gravity there because it was the weight of the water or the fluid displaced. I forgot G. I think I forgot G last time too.
No, you wrote those.
Oh yeah. I'm sorry. You're right. I forgot that. Should have been a G factor there for 9.81. Okay? Now, great. So we have expressions for all of these. The last little thing that I need is what? How do I use all this information to? I mean, ultimately, I want to solve for something, so I need an equation. This is a diagram. It's not an equation. How do I get an equation? Like, is there a law of nature that might help us here? Okay, yeah, so I'm really using Newton's second law. The net force equals mass times acceleration, which is 0, because they're not moving. That's where you get the actual equations. It's all kind of build up. The equation is going to say 0 equals the normal force from the person plus the weight of the balls plus the buoyant force. And then you have to solve for the number of balls. Okay? Great. Go ahead and do that. I have no idea what you got there. I assume it's bigger than 2. If you don't get an answer that's bigger than 2, we might have made a mistake. Is there anyone who's stuck? If you're stuck, raise your hand and I'll come around and help you figure it out. Sapan, are you doing okay? Okay. Nobody says they're stuck. Last one. Possible. Think about a beach ball like this. If you jump on top of it, you don't weigh enough to submerge that. You know, to really like submerge it fairly, you know, fully submerge it. You couldn't. I don't even know. Probably a Nerf or like a football, you could submerge, but maybe not three. It's hard to know because we've got three.
People.
That's good. Okay. 1,000. Ball, you should have ball. Let's do it a different way. 4/3 pi. Oh. Yep. He had a smaller number, but yeah, I don't. I just know it can't be small. I don't know how large, so let's kind of run through it. But tell you what, I'll just do it. Okay, let's go through it and run the numbers and see how we fare. I should have recorded this one out before. Okay, so to do this, I'm going to have the buoyancy force. So my equation is going to be 0 equals the buoyancy force, which is 1,000 times G, 9.81 times, let me make sure I did that right, 4/3 pi r cubed. So that's 4/3 pi diameter cubed over 8. So that's pi over 6, yeah. Right. So I agree with that. So I'm going to have pi times diameter cubed. So that's going to be 0.06 meters. I have to convert from centimeters to meters. Cubed, don't forget the cube, over 6 times the number of balls. Can somebody calculate that number? Let's see what you get. This number, we're getting 1.11, okay? And it would have units of newtons. Make sure did everybody get that same result? Okay. So that's that. So that's the buoyancy term. Plus, so that's the upper one. Now I have the downward forces. So I get 0 is minus, and I'm going to get 735 minus, I'm going to get 0.0981 times the number of balls. So what do I immediately notice? This is like 1. And this is a contribution from the mass of the balls. It makes a pretty small effect, actually. We probably could have just ignored the fact that they had mass. We would have been pretty close. But all right, we've got the information. We'll just keep it with us. So I can rearrange this to say that 735 equals 1.11 minus 0.0981 times the number of balls. That's pretty darn close to 1. So it's going to be essentially number of balls should be about 735. Oh, I'm getting. Is that within kind of rounding here? Is it, you guys, did I mess it up? Did you guys agree, I guess, is the first question, make sure I didn't mess it up. You get the same thing? Okay.
I don't think it got that far. So I don't think it pretty good.
Okay, so that's, you see how I arrived at this result. I'm regrouping here these terms because they both have the same variable, number of balls. It's going to end up being about 1 times number of balls has to equal 7. Zach, you were going to say something? No. All right, Alex? Okay. Billy, what did you get? What number did you have?
I messed up
The stuff.
buoyancy.
What did you have?
I ended up getting 2.22. I divided by 3 instead of 6.
Oh, okay. It's going from radius to diameter and that.
Yeah, between that and the negative signs.
Okay. All right. Safon, did you get the same result? Okay. All right. So that's how you can use buoyancy. And you'll have problems kind of like, I mean, it won't maybe be ping pong balls, but the idea is it's just another force. And to reiterate, the buoyancy force equals what? What's the phrase you should say to yourself? You should say that phrase every time and then figure out how to mathematize it. The buoyancy force equals the weight of the fluid which has been displaced. Okay? So if something is fully submerged, then the volume of the object equals the volume displaced, if it's fully submerged. If it's only partially submerged, you have to figure out that fraction of
So
volume.
because the balls are fully submerged, it's
So then it was there. But if I had said, oh, only let the balls be half displaced, you'd have to figure that out. And that would just, really would just amount to a factor of half here. But you have to read the problem to analyze it. Okay? All right, let's take a mass break. Okay, Stefan, we'll take a 5-minute mass break. So Bernoulli's, so we're going to talk about Bernoulli's equation, Bernoulli's principle, and this is how we're going to see fluids that actually move. Before we dive into that, I just want to review what's a little bit of vocabulary. What is the volume flow rate? What does that measure? What is volume flow rate? That measure. Volume flow rate. We saw it last time. Change in volume with time, yeah. So the idea is, you know, you're enjoying the nice rainy, cloudy day, and you go sit down by the Chattagoyne, and you're just watching the water go by, and you're saying, okay, as I sit here in my chair watching the water, in a certain amount of time, how much water goes by? What's the rate of change of volume of water with respect to time? So, you know, in 1 second, there are so many meters cubed of water that flow by at any one time. Okay, so we have volume flow rate. Oh, not really. Volume flow rate. I don't know if that's any better. You guys see that? There's two. Okay. Pretty faint. I got some new ones, but usually when they're new, they're all the volume flow rate is just the rate of change of volume with respect to time. I will use this kind of oversized, exaggerated capital V for volume so that there's never a doubt, because we're going to have lots of V's this course. I don't want you to get confused on this. So the volume flow rate or volumetric flow rate is, so it would be the rate of change of volume with respect to time, but it equals the area times the speed, really. And I'm going to write that in an exaggerated fashion, so you never get confused with velocity versus volume. Okay? We had another concept, which was what? It wasn't the volumetric flow rate or the volume flow rate, it was the mass flow rate, m dot. M dot, the mass flow rate. And it'd be the rate of change of mass with respect to time. And assuming the density of the fluid in the little region you're studying doesn't change, you can say that this equals the density of the fluid or material times the volumetric flow rate, which means it equals the density times the area times the speed of the flow. Is that okay? Now, in steady state, which is what we will always have, even when things are really complicated for this semester, in steady state, mass in is mass out. It's like toothpaste. You squeeze one end and it squirts out the other side. Right? It doesn't hide. There are no pockets to store mass and build up. So anything coming in is going to push something out on the other side. So the mass that goes in, m dot, the mass per second in, so m dot on the way into a pipe or a component is going to equal m dot on the way out, 1-to-1. That will be true always for us. However, when we have an incompressible material, if it can't, it's not squishy in any way, then we know that the densities are constants, right? Because if it was compressible, you could squeeze that mass into a smaller region. The density would change. So if it's incompressible, then rho is constant, and therefore m dot being the same as it goes through a pipe on the way in and out means that v dot must also be the same on the way in and out. No? Does that make sense? Not okay? So let's imagine we have a pipe. We have two sides, labeled them 1 and 2. And the water, it comes in, and then it comes out the other side. All right? In steady state, we're going to assume that the mass in per second is the same as the mass out per second. All right? So I get m dot on side 1 must equal m dot on side 2. That's steady state for us. It'll be more than that, but for right now, that's what we have. That's part of it. Okay? Now, but just write this down. This is going to mean the density on the left times the area on the left times v dot. On the left must equal the density on the right times v dot on the right. That's just using the definition. I'm not doing anything. I'm just defining things. But now what I said was, if the density is uniform everywhere, and it's incompressible, so it can't change because there's no way to change the density would mean to somehow compress things or stretch things. So if that can't happen, then the densities are the same if it's incompressible. I'll write that here. Incompressible. You really don't need that. You really just need that it's the same, but incompressibility is going to be an assumption that does that for us. Then that would mean, do that in green, that these are the same, so you can just cancel them and get that V dot is the same. So now, we see that. If you have an incompressible state and nothing changes on that, then M dots can be converted into V dot equations. M dot equations can be equal. All right? Logic on that, okay. Okay, great. Now, we're going to imagine that we have a segment of pipe. So you can have any shape you want. You can imagine the size changes on either end. So you could have on this side, we'll call this side 1, we'll call this side 2. You can have area on side 1, and over here we have the area on side 2. That'd be fine. And then what you have is that there is you think of it as like a hockey puck or something of a little chunk, a segment of the flow which is being pushed in. Kind of in this region, it's being pushed in, and as that happens, it's going to squeeze out another segment on the other side. It's going to be squeezed out. So as this goes in, it's going to knock out some more. Okay? Is that all right? So the first thing we want to do, well, okay, so we've already talked about the volume and mass. We've got those equations. What other property have we talked about this semester? Really only one other thing that we're going to use to describe stuff. We're not going to talk about positions of particles and things like that. We don't talk about positions and acceleration so much. What will we talk about? Well, energy. We're going to talk about the energy. So what I want to do is study the effect, or study the energy in this situation. So, all right, so first off, let's think about this. So, this is part of some long hose, garden hose or something like that goes off. So why does the flow move forward? Why did this little segment get pushed in? There's some more behind it. So something pushed on it, right? So that means that this chunk of fluid is being pushed on over a distance. What happens when you push something over a distance? There's work. Yeah, there's a work being done by this being pushed into the pipe. On the other hand, as it leaves this segment, what's happening? It's pushing on the next segment, right? So it's doing work simultaneously. So you're going to have, if we're talking about work on this chunk of fluid, you have a positive work here and a negative work there. So you're gaining, there are two works involved, and there's a minus sign issue. Okay? So let's see, so we need to understand the work. The work, let's just focus on, well, let's just focus over here on the left. So the work at 1. What's the formula for work? Okay, really it's an integral, but remember, I'm going to make these really thin I'm gonna take a limit and kind of, these are differential size hockey pucks eventually. So then, instead of, you don't have to do the integral, it really is force times distance, and distance is gonna be baby steps. Okay? So that's gonna be work, or if you wanted okay, I'll just, work is gonna be the force times the distance. So I'm gonna say, over here I've got delta x1, and over here I'm gonna have delta x2. So the work is going to be the force on side 1 times the distance that the fluid travels. Awesome. Why is that not? So that's a fine expression as long as the force is constant, which we would assume it is. Why is that not a convenient way to parameterize things if you're talking about water flowing in a garden hose? I don't know about you, but when I look at my garden hose, can you see the fluid? I can't see the fluid, right? It's hidden. So I can't really measure delta x because I can't see it moving. So that, it's not wrong, it's just not, maybe, it's not going to be the best way to write this. So instead, we are going to change variables, and we're not going to talk about positions of chunks of fluid. Instead, what are we going to do instead? What could we?
Speed.
You could do speed. We could also do volume because we know the area. So what I can say is this. I can say that this, I'm just going to multiply and divide by area. I can say this is area at 1 divided by area at 1 times the force at 1 times delta x1. Okay? I'm doing nothing in a slightly clever way. And then I can just write that as force at 1 divided by area at 1 times area at 1 times delta x at 1. Everybody see what I'm doing there? Questions on that? Why would I rearrange it this way? What does that start to look like? What is it? Force over area. What is force divided by area? Pressure. Pressure, right? So this is the pressure on the left-hand side. Right, side 1. What is this? Well, that's just the volume that we pushed in. So this is, if you want to change your volume at side 1. It's how much volume of fluid has been added there. I think in my notes I just called it, no, I didn't call it delta V. Okay. You can see how I did that. I really just kind of multiply and divide by area and rearrange things. It turns out, let's box that. For fluids, instead of saying force times distance or integral of force over distance, the work is going to equal, in general, the integral of P dV. That's the general calculus expression. I'm giving you the algebraic version of it, but that's really the formula. So just like in high school you memorized work is force times distance, and in last semester hopefully you memorized that work is integral force over distance. This semester, this is our main formula. We will use this over and over and over. So burn that in your brain. Right? When we talk about a car engine, a piston pushes and we're extracting work, that's the thing. Right? That's the thing we have to evaluate. So you got to know that formula. It's going to be a big one. All right. When things are constant, pressure pops out and just becomes delta V. All right. So coming back to our story then, on this side I'm going to have positive work. On this side I'm going to have negative work. Okay. So the net work, net, W net, is, nope, we don't know. I know that the density is the same. I know that the volume flow rates, I'm going to assume that it's the same, but I don't know about the work. What I do know is that it's P1 delta V1 minus P2 delta V2. That's certainly true. And then I'm going to assume, I'm going to use the fact that V1 or delta V1 equals delta V2, assuming what is that? Yeah, what is that really an assumption about? No, definitely not constant velocity. Incompressible, constant density. This is the density 1 equals density 2. That's what that means. So even though the problem doesn't, it may not tell you that, but that's what it's actually meaning. There are a lot of equivalent ways to state these assumptions, and so a problem will maybe not give you all of them. You have to read it and know what it's actually implying. Okay? Constant density implies these are the same, so I can write this as P1 minus P2, and I'm just going to call it delta V. If all the changes of volume are the same, no point labeling them 1 or 2, they're just all the same. Okay? That's the work. So we don't know that the pressures are the same. We have no reason to think that. We just don't know. What we do know is that the volume per second has to be the same. So that's what I can say. Okay, that is the work being done on the fluid. Okay. What we have to do next is to think about, well, okay, let's go back to the work energy theorem. What does the work energy theorem tell us? Work equals what? Work equal in the work energy theorem. What we talked about last week. Work equals change in energy. Change in energy. Okay. So I know that work equals the change in energy of the system. Well, the system is going to be the fluid in the pipe. So what is the change in energy of the system, of the fluid in the pipe? Okay, yeah. So it's that. That's going to be the left-hand side. What about the right-hand side on that? Well, what kind of, it's little droplets of water. What kinds of energy can it have? Assuming there's no viscosity and the droplets don't talk to each other. No. It can have a kinetic energy, and it can have a potential energy. It's moving in height. It can, garden hooks can go up or down, whatever. So I already know the formula for work. Now I need the formula for the change in energy. So the change in energy would be the change in kinetic energy inside that fluid, and plus the change in potential energy. All right, so that's really it. Now, here's the thing. In steady state, one droplet pushes another droplet, pushes another droplet. But if you look at what's happening right here, there's no real change happening right here, because it's kind of like every time something moves out of the way, something equivalent just takes its place. This internal stuff doesn't really matter. The pluses and minuses cancel out. So the change in energy of the whole system is going to, well, it leaves, the ending state is the stuff as it leaves. And the initial condition of the stuff is the condition at the input. So it starts like, with the temperature, well, we don't know about temperature yet, but it starts with whatever pressure and velocity it has here, and it finishes with whatever pressure and velocity it has there. So to figure out the change in energy for this whole thing, you really just want to say the energy on the way out minus the energy on the way in. All right, yeah. So in the stuff that happens in the middle, the pluses and minuses cancel out. So we just have to focus on the inputs and outputs to figure out the overall changes. Is that okay, or no? It's kind of like if you go to a movie theater, first of all, they're all closed right now, but assuming they're open, and you're tasked with keeping track during the movie of the number of viewers. Do you have to monitor the entire theater to keep track of that?
Just the entrance.
Just the entrance and exit. It's the same exact idea. There's no, if I want to monitor the energy in this thing, I don't have to keep track of the middle because there's nothing happening there. If I just want to keep track of pluses and minuses, I just look at the exits, entrances and exits. That's it. The same idea. Okay? So that's what we're going to do. This is going to simply be the kinetic energy when it leaves, to be the mass that as it leaves. We'll kind of turn this into a fluid expression here, times the velocity, when it leaves. So that would be, so this is V2, because it's leaving, minus the kinetic energy when it enters. And then for potential energy, you could have complicated potential energies. Yeah, I don't know, but charges and things. But we're just going to have gravitational potential energy from primitive physics. So that would be plus potential energy due to gravity. That's mg times the height when it leaves minus the potential energy when it enters. Okay? You see where I'm trying to motivate these terms. You see where I'm getting it from. And I'm going to turn these into fluid kinds of things. So what mass should I use? And things like that. That'll come from fluid stuff. Do you have a question? I was just putting that in there to try to trick you. Thank you. No, I messed that up. Did I screw any other? Are there any other confusion? No, I'm messing the other ones and twos up. Okay. Let's figure out what mass should we be talking about. Well, we're talking about the mass when it leaves. So that would be 1/2 the density of the fluid times the change in volume as it leaves. That's how much we have. And here the velocity is there. Minus 1/2, and be the density. And again, it would be the density as it leaves, but we're assuming the densities are uniform and constant, and it's incompressible. So it's the same density both places, times the volume as it leaves, so it's the same, times the velocity squared plus same rho delta v times g y2 minus rho delta v times y2 or y1. Oh, that looks terrible. I screwed up again. Thank you. All right, so now I want to regroup this because there are common factors around here in a lot of this. So I'm going to equate the left-hand side and the right-hand side, but I see that, look, on the work term, there was a volume, and on every term here, there's a volume, so I can divide that out. So I can cancel, well, maybe I should write it out. You know,
All of these have arrows.
all of these have arrows.
Bars.
Thank you. Yeah. These are velocities or speeds. These are volumes. Volumes and velocities. And you better keep them, I mean, they enter with different powers, so it matters. If you equivocate, just call all V's the same thing, you'll be in trouble. So when I write this down, I have to write down the work equals the change in the energy. So that says that P1 minus P2 times delta V equals, everything here has a delta V, so I can factor that out. I'm just going to factor out the volume factors. So that's going to be 1/2 the density times V2 squared minus V1 squared. Now I got, those are velocities. Plus rho times G times Y2 minus Y1 and all that should be times delta V for volume. I'm regrouping, just pulling out common factors, trying to compress this as much as I can. So the kinetic energy, the velocity squared pieces, since the density is the same, it's incompressible, we just might as well pull it out as a common factor. And the same way with the potential energy terms. Yeah?
For that last one, is that a row or a key?
It's a row. Yeah, it's a row. My rows will always have the tail. My P's will be Latin. Okay? Now, the volume factors are the same, so those cancel. And I'm left with the following equation. I'll write it in a couple ways. I could write it as P1 minus P2 equals 1/2 rho times V2, velocity 2 squared, minus velocity 1 squared, plus rho G Y2 minus Y1. Okay? This is called Bernoulli's equation. This is Bernoulli's equation, the goal. But I'm going to rewrite it in a couple ways that are maybe a little bit easier to remember. Notice on the left-hand side, everything with a 1 has a plus sign, and everything with a 2 has a minus sign. And on the right-hand side, everything with a 2 has a plus sign, and everything with a 1 has a negative sign, which means you can rewrite it so that all the 1s are on the right and all the 2s are on the left. Is that, I think I got it backwards for you. On the right and left. So 1s will be on the right or left. So I could rewrite this and write it as, and this is the way I personally remember it, P1 plus 1/2 rho velocity 1 squared plus rho G height 1 equals P2 plus 1/2 rho times V2 squared plus rho G Y2. I find that that's an easy way to remember it. So that I can always remember there's going to be a pressure term, there's going to be a kinetic energy kind of term. It isn't mass, it's density, but okay, whatever. And there's a potential energy term. I can remember that. And then I just remember, but then it's a question of minus signs. How do you get those right? When you do it right, all the quantities from one side come together with plus signs. And then everything on the other side also has plus signs. Okay? That's how I remember this.
Just grouping the differences as delta. It's second step there.
Here, you could call it delta of v squared. But the problem is then you have over here you have to say this is minus delta. So if I write it this way, there are never any minus signs. So I never have to question did I put it in the right spot or not. I just remember that if I put all the 1s on one side and all the 2s on the other side, there are no minus signs. Stop. Questions? Okay. There's one last way I'm going to write this, which is in a lot of books. This is some like imaginary segment of pipe. I didn't say it was anything particular. It's not necessarily the end. It could be anywhere in the middle, which means if there's nothing special about this point or that point, then in fact, they could be any point along the flow. There's nothing special about point state, 1 or 2. They're just random points. Another way to write this thing is the following. Sometimes people just say P plus 1/2 rho times the velocity squared plus density times g times the height equals a constant. The idea is, this is saying this is all information that lives on one side. It all lives on one side. This is all information that lives on the other side. And they don't talk to each other because, it's just water droplets. So therefore, the only way that stuff here is related to stuff there is they must just be a constant, because there's no way that they could dynamically be talking to each other. So they must just be a constant value the whole time. And this is a really common way to see Bernoulli equation. All of these are called, all three of these are called Bernoulli's equation. Bernoulli's equation. Okay, pressure plus 1/2 rho v velocity squared plus rho g y is a constant. That's Bernoulli's equation, or Bernoulli's principle. Okay. Questions about that? We're going to go through what that means here in a minute, but let's recap. How did I get to this point? What were the assumptions I made? No friction, right? I didn't talk about friction, viscosity, any of that. So we're in this magical, mystical unicorn fluid. I guess you had to blend up a unicorn or something. What else did we assume? What was the other thing we assumed here that helped us simplify equations? Incompressibility, right? That was, so if you have a boiler, right, and something's being turned to steam, you can't use this because more's going on there. You have to deal with that, right? So this is like, we're talking about your garden hose, right? That's what we're talking about, right? The water on the way in is chemically and whatever. It pretty much looks like the water on the way out, right? There's nothing happening there. Okay, that's what we're talking about. Okay? Now, that being said, in some of the problems, and sometimes when you're trying to get rough numbers, people will use this for air or steam. Now, that's not incompressible, right? So it doesn't, strictly speaking, hold, but as long as you have steam, but maybe the temperature doesn't change much, then the densities are approximately the same on both sides, and then it approximately holds. So when you want to apply it to a gas, it's fine as long as you understand what you're buying, right? When you make that assumption, you're approximating and saying that various properties are roughly constant and it's close enough. Okay, so, okay. Let's talk about what this means. So we're going to imagine we have a pipe which does this. Okay. You know what? We'll do these in two stages. We'll separate the gravity. And we have our two equations now. What are the two equations what are the two things I can say about this incompressible fluid? One is Bernoulli's equation. Pick one of those, they're all equal. There's one other thing we know. You might even have started with it before we got to Bernoulli's equation. What else do we have that was constant throughout? The volume flow rate. Right, we have the volume flow rate. So we have the volume flow rate says that A1 times the velocity at side 1 equals the area at 2 times the velocity at 2. And 1 and 2 could be any points in the fluid. They don't have to be the end points. I can make this 1 and I can make this 2. These are arbitrary points that we're talking about. And on the other hand, I have the Bernoulli equation, which says that P1 plus 1/2 rho velocity 1 squared plus rho g y1 equals P2 plus 1/2 rho velocity 2 squared plus rho g y2. These are really your only two equations. 2. That means how many unknowns can you possibly hope to solve for at most? 2. Right? So if you start reading a problem, you think you've got more than 2 things to find, they must actually be somehow secretly telling you that stuff in the problem. So read it again. Okay, let's talk about what happens here. On this side, here's a pipe. Let's make this state 1. We'll make this state 2. Make it, and so is water, something that's incompressible. What do I learn from the first equation? What happens?
Velocity on 2 is higher.
Hmm?
Velocity at 2 is higher.
Velocity at 2 is higher. Think about that. So the area here is bigger, which means the velocity at 2 must be bigger. So that's kind of counterintuitive to me. You think of, oh, I'm pinching it, the velocity should shrink. But in fact, in order for the mass to not pile up, as long as since you have the mass in is mass out, what that actually means is if you reduce the area, then it has to sneak through faster. If you think about, has anybody baked a cake before? Okay, you got that mixer, and if you kind of pinch that mixer near the edge of the bowl, that fluid seems to go faster when it pinches. That's kind of the same thing. You've got, when it's out in the middle, the fluid, it's flowing around the beater. But if you were to pinch it, it kind of speeds up. You can kind of see that happen. Or, let me see. I don't think we have any. What's that?
It's like putting your finger over the end of a hose.
Yeah, okay. There you go. Yeah, that's a good one. So you have a garden hose. Right, here's a garden hose. The water's flowing out. And it just dribbles. Right? You want to hit your flower. Right? So you want to hit the flower that's farther away. It's not going to make it. What do? You pinch the nozzle there, right? Pinch the nozzle. So roughly, if you kind of think about that, that means as you squeeze that nozzle, that means that the exit velocity increases, which means it leaves the bigger horizontal velocity. And then if you think of it as like a physics 1 problem, if it's going faster, when it leaves, it's going to travel farther. And that's why, that's what you see. That's a good example. If you squeeze it, the velocity increases. Okay? So that's the first observation. Now, so velocity at 1 is smaller than velocity at 2, what about the potential energy at 1 versus 2? Are they significantly going to change? No. And I will just tell you this, if you plug in numbers, basically, if you're talking about pipes in this room, this term is parametrically smaller. It just doesn't, it's negligible compared to everything else, almost always. Unless the problem really draws it out and says, calculate this. So they really indicate that, almost always you can ignore potential energy. Unless you are talking about designing a well, or, a pump, it's like how you're talking about piping things over a mountain or something like that. Mostly you can ignore the potential energy term. Mostly. All right, so assuming you can ignore that, in this case you can because it's a horizontal pipe. If it's horizontal, then there's no change anyway. So now, what does Bernoulli's equation tell me? So over here I had that the velocity at 1 is less than the velocity at 2. That came from the volume flow rate equation. What happens with Bernoulli's equation? If you ignore potential energy, if velocity at 1 is smaller than velocity at 2, what can you conclude about the pressures?
P1 is higher.
P1 has to be higher. So pressure at 1 is greater than pressure at 2. There's a pressure drop. So when the air flows faster, the pressure shrinks. That's kind of also maybe a little bit counterintuitive. So we have that pressure at 1 is greater than pressure at 2. You guys think, are there any examples you think of that will make that, explain that? You think of a everyday situation? I have one in mind, I'll show you, but maybe Sydney came up with a good one there. So think of a situation where you've seen that, where something goes, as the pressure, as the air goes faster, the pressure drops. No?
It has less to bounce into, maybe?
What's that?
Does it have less to bounce into? As far as like there's more liquid on 1 to bear down on it than 2?
I hadn't really thought about that. Let me think. I don't want to. I can see where you're kind of thinking there. I haven't thought about that. Let me think about it. I don't want to say. I won't commit to it yet. But that's something that you're thinking about. Well, here's one. Who's seen Mary Poppins? Yeah, the original one. No. Zach.
I've seen
All
the
right.
original.
Forget the lab on Friday. We're going to watch Mary Poppins now. Okay. What happens to the kid when he puts the broom up the chimney? He gets, all right, he gets dirty, yeah, but he gets sucked up the chimney. What's going on there? Has anyone ever cleaned a chimney? Yeah? Was it on a windy day? No, okay. All right, so what we're going to do, when you guys signed up for the class, they gave you an official wind speed tester, right? What? Yeah? All right, here you go. The phone. I can't give it to you. Just need a piece of paper. Ooh, crap. Masks. All right, you have to try this at home. I will do it up front. Yeah, but if you're blowing things, like musical instruments, it's supposed to be 12 feet. All right, so I will get 12 feet away from everybody else. I will remove my mask. Dun, dun, dun. Okay,
Lights on.
so it fell. Pretty impressive, right? Awesome. Ready? Just to make sure I'm not doing anything really fancy. It fell, all right? Why did it fall? Gravity. Yeah, you're right. Now, what I'm going to do is blow across the top of the piece of paper. What's going to happen according to our formula here? If I blow across the top, I'm going to assume Bernoulli's equation works. It's approximately, because it's all that stuff. As I blow across the top, I am increasing the velocity on the top. So the velocity is going to be bigger on top than it is below, the velocity of the air. What's that going to do to the pressure? So the pressure on the top will be smaller than the pressure below. So if you have more pressure underneath than you do on the top, which way is the net force going to be? And it'll rise. It rises up. So what's happening there is I'm increasing the velocity, which causes the pressure to drop on the top, which means the net force is up. Okay? Is that? Yeah, it doesn't work so well with the mask. All right. So, well, we're almost out of time. So when class is over, you guys can use your paper and do it on your own time. Socially distance. Okay? All right. So that's one thing you do. So when you're looking at the homework, this is more for the homework for next week, because we're going to have conceptual questions on this. Literally, that's what they're getting at is you squeeze it, the velocity goes up, the pressure drops. That's what they're having you look at. Same thing happens, tornado causes wind to blow across the top of the house. Now, obviously, sometimes the pressure's on the side of the house. Oh, sorry. Side of the house, and it knocks the walls in. But let's just ignore that. Assume that's not a big problem. Wind blows across the top of the house. What does it tend to do to the roof? Lifts it up. Yeah. Airplane wing. Turns out that one's harder. More intuitively, yes. It turns out that one, though, doesn't work. What I'm talking about here is true. There's no turbulence, right? It's perfectly nice, steady flows. It turns out when you get into it, it's a Calc 3 problem. If you don't have turbulence, when you go through, you think that that's going to be true for an airplane wing, but if you don't have turbulence, actually, it won't lift. So you feel like, so people will say, oh, you make it an airplane wing kind of teardrop shaped so that a flow has to travel farther across the top of the wing than it does across the bottom of the wing, which means it must be traveling faster across the top of the wing than the bottom of the wing, which means the pressure at the top is smaller than the pressure at the bottom, and you have lift. It turns out, though, when you calculate, you have to calculate something called circulation. It'll be like what you do the last 2 weeks of Calc 3. It equals 0 for an airplane wing. Right? So that actually, it intuitively feels right, and you'll see that written on the web that's why an airplane wing travel flies, lifts. What's more complicated, you actually have to have turbulence to get it to lift. So I don't want to tell you something not true, even though it feels like it should be right. It's more complicated. Okay, let's just see, well, we're about done. What if I did add back the potential energy terms? If you increase the potential energy terms, then that's going to tend to suppress the balancing terms. So there are a lot of problems you can do qualitatively just by saying, okay, this thing is constant. So if you increase this, you expect these things to start maybe decreasing. And so there are all these comparison problems you can do. Okay. Next class, we're out of time. Next class, we're going to do a lab on buoyancy using stuff we've seen. And I'll probably throw in some practice problems on Bernoulli's equation where you can kind of go through these different scenarios, evaluate some numbers. Okay? See you guys on Friday. Homework due Friday. We'll do lab on Friday. No class on Monday, right? Monday is a school holiday. It's Labor Day. Okay? Sapon, did you know about that?
I didn't even know about that.
So I'll see you Friday, and then it'll be Wednesday after that.
So, which
See you guys.
scan for your phone did you say you?
You'll be-